afternoon is Carlos Simpson, who will tell us about infinity categories and why they are useful.
Okay, great. So thank you very much. So thanks very much to the organizers for the invitation, and also for suggesting the title too. So I'd like to try to explain basically kind of how I think about infinity categories. Okay, so infinity categories. And so this is going to be mostly about infinity-1, what's called infinity-1 categories. I'll explain that maybe later. We'll see along the way, we'll see a little bit about going to infinity 2 and so on, infinity n. So the question here is sort of from a point of view of somebody who's interested in algebraic geometry. So from the point of view of algebraic geometry, how do you get into this kind of thing? So I'd like to say that because mostly what I'll say, at least today, is going to look a lot like algebraic topology, I think. Although I'm not that much of an expert in algebraic topology. But so let me just start by saying that what's the kind of basic motivation? So I think the basic motivation is that we're going to start with some kind of Grothendieck site, basically. So if x is a Grothendieck site, then we know that it's useful to think about sheaves on X, okay? So what's a sheaf on X? In other words, a functor from X op into sets that satisfies some kind of descent property. So now, it turns out, so I'm not sure I'll explain this, but it turns out that it's also good to look at what might be called sheaves of spaces. So this is going to be functors from X op into spaces that again should satisfy some kind of descent property. And this theory was provided in its technical sense by Jardine, basically. By Jardine, so Jardine was kind of based a little bit on Joyal. And in turn, Joyal, if you look at, so for those of you who might be fans like I was, especially a long time ago, of Grothendieck's book, Pursuing Stacks. If you look in Pursuing Stacks, at some point in this collection of letters, there are some letters of Grothendieck to Joyal where he says you should be able to do this kind of thing, and Joyal writes back, oh, we already did that, or something like that. So it's kind of unclear whether that, I mean, from Grothendieck's point of view, he was the one who thought of that was a good idea. Maybe Joyal already knew that that was a good idea. So we'll be explaining this in a little while. But so what I like, so to manipulate this type of thing, to manipulate these objects, we basically need some kind of theory of infinity categories. So you can think that, I mean, it's not really surprising, you might say, because this is some kind of homotopy theory data. So we're trying to think of a sheaf of spaces, but where we don't care about the difference between homotopy equivalent spaces. But since the relation of homotopy equivalence is kind of a very flexible one, that's a sort of a subtle situation, and that's basically the thing that requires the theory of infinity categories. So there was previously, a previous thing of the same similar thing. Previous similar question. Is just the derived category of complexes of sheaves. So if our site has a ring or something like that, some kind of, maybe not necessarily even bounded, some kind of derived category of complexes of sheaves. So a complex of sheaves, roughly speaking, maybe very roughly speaking, but so a complex is thought of as a functor from X op into the category of complexes, say of Z modules. So here, of course, if you wanted to say complexes of OX modules, then you'd have to say that your complexes here actually have a structure of OX modules, so that's more of a relative thing. So it's not really a functor into a single category. But just as a basic idea, this category of complexes is kind of similar to the category of spaces in the sense that you might have two different complexes that are homotopy equivalent or quasi-isomorphic, and you'd like to say that those are the same complex. The problem is that how they're the same is going to be a choice, and then the sameness between the sameness and so on, that gives you these higher homotopy. So it should be pointed out that this theory was kind of pretty successfully treated already without really using infinity categories, and continues to be pretty successfully treated without necessarily using infinity categories. So in this case, there's maybe a little bit less need for some kind of infinity categories. But I mean, I think at least one current of modern thought, which I think is you're seeing in the discussion of derived algebraic geometry, is that it's also useful to apply the infinity category viewpoint even to this situation. Okay. So that's just a sort of a review of the basic types of.
Can you say a little more what you mean by successfully applied in this context? We're talking about the ordinary theory of the derived category.
The ordinary theory of the derived category continues to.
Okay.
And so,
you're not talking about further attempts to like glue these things together or using derivators that these sort of had in mind, but.
Yeah, I mean, those are, yeah. There's a lot of different ways you can, prove the theorem that you want to prove, you might say. And I think, so this is one of my main worries for this week, I should say. The goal here is to avoid saying that you absolutely have to use some kind of a theory like infinity categories or any other theory. I don't think that's really true. You don't absolutely have to use anything that, so I think so there's a question of, what are we trying to say here? So I think the point is, what I would like to say, if possible, is that it's more a question of observing that there's certain phenomena that show up. and then the notion of infinity categories is sort of a way of packaging those phenomena. So that's why I would like to explain now. So what happens here, just in a nutshell, is that it turns out that the enhancement of this category in some cases is actually unique. The infinity category enhancement of this usual derived category is in some cases unique. So there's some kind of rigidity there. So that kind of indicates that you might be able to prove your theorem without actually going through the enhancement. Okay. And that happens in practice. So what I'd like to say here is that it's more on the level of let's kind of observe there are certain phenomena that show up. And then I think in other cases, that turns out to be what you might call an accelerator or something like that. That if you then use the theories of infinity categories that show up when you look at these phenomena, then you can start saying stuff at a higher rate of speed, at least in any case. So let's try to understand what's the basic phenomenon that's happening here. Okay, so this is the slogan here. The slogan is that localization creates homotopy. Okay, so I'd like to draw a picture here to show how this is true. So suppose we have two maps. Suppose in a category. So we'll start with a category. So by localization, I mean localization of categories. So we start with a category C, and then we choose a subset of maps. So you can think of this as maybe a subcategory of C, not a full subcategory, but just some collection of maps. But you could just also think of it, or So here I mean a one category. Okay, make that precise. But yeah. So this could just even be a single map, as we'll see in the picture. Then you'd like to say, let's just make those maps invertible. So let's force. Let's force the maps in W to become invertible. Okay, so now let's draw a picture of what can happen. So what can happen is we might have two maps. Let's see. We might have two maps from X to Y. Okay, so and we might have another map from Y to Z. Now we have, but our category might have the property that the two compositions are the same. So let's call this maybe H. So maybe F composed with U equals F composed with V equals H. Okay. And now if we put F inside W, then when you invert F, this forces you to say that U equals V, right? Because if we take F inverse composed with H, that's going to be F inverse composed with U, which is, composed with F composed with U, which is U, but it's also going to be equal to F inverse composed with F composed with V, which is equal to V. So if we take so the basic picture is if we take a diagram like that, if we sort of make this arrow fuzzy, so that tells us we would like to invert that arrow so that we're saying F is inside W. W is like sort of a subgraph of the graph of C. That tells us that U is supposed to be equal to V. Okay? So we can kind of visualize this by drawing drawing in these there's two cells in this picture. In the nerve of the category, there's going to be a 2 cell that says that F composed with U equals H. There's also going to be a 2 cell that says F composed with V equals H. Okay? So there's 2 different 2 cells. You have to imagine, right? So this is going to be like a little cone. And so that's going to tell us that U is supposed to equal to V. Now, suppose we have a different map, okay? So suppose that G composed with U equals K, and G composed with V equals K. And suppose we put G inside W also. Then G also tells us that U equals V. Okay? So just think of the other two cells here. But so now we have U equals V in 2 different ways, okay? So now if you take 2 points and you say that the 2 points are the same, let's draw it over here. You take 2 points, you say that the 2 points are the same. You're going to sort of say this equals that, right? This is U. This is V. And we say that and then on the other side, we have somebody else comes along and says, okay, they're also the same. Okay. Well, what do we have here? We have a circle. Okay. So this creates a circle. This creates an S1 in the maps. Okay. So, and that's kind of really the basic, I think, thing which is going on here. That's the basic thing which is telling us that we sort of we're bumping up in the homotopy theoretical world when we start localizing maps in a category. Okay. So now, how might you see that this is happening? So you can still see that this is happening in the world of 1 categories. So to see that this is happening, we might have sort of a fibered category over C. So I'm not sure whether this is fibered or co-fibered or something like that, but anyway. We might have some kind of fibered category over C with the property that the pullback maps like F upper star from the fiber of F over Z is an equivalence of categories with F over X over Y. And the the G upper star from the fiber of W is an equivalence of categories to the fiber of Y. Okay.
Sorry, can I ask a simple question?
Yeah.
So on the right we have, it creates an S1 that maps from X to Y, but on the picture on the left looks like an S2.
Yeah, so I'll be discussing that in a minute. That's a good question. Let's keep that question for a while. That's a perfectly good question. In fact, thank you for pointing that out. So what he said, here we have an S1 that's shown up, whereas in this picture, this looks like an S2. Okay, so thank you, because I was going to try to say that, but now that a member of the audience, I did not plant him there, okay? Now that a member of the audience said that, so that gives some additional weight to that observation. But we're not quite ready to talk about that. So suppose we have like a fibered category over C, and we have and suppose that the pullback maps have the property that they're equivalences of categories. Right? The fiber category, we have these category fibers and so on, and pull back maps. Well, this is going to induce, sorry, I didn't really do the calculation here, but this is going to induce a natural transformation. In fact, a natural isomorphism of maps, of functors. Well, let's put it this way. This is going to induce two different natural isomorphisms of functors. So we have, let's put this up here. Well, we have the U upper star goes from Fy to Fx, and we have the V upper star. Right, we have two different pullback functors from Y to X. But, well, you have to do the calculation, but if you say that you have a fibered category, you can sort of believe this. You have a fibered category and you have this property that this is an equivalence of categories, then that's going to induce the sort of the pullback of H is equivalent to the pullback of V times the pullback of F, but it's also equivalent to the pullback of U times the pullback of F. Since pullback of F is an equivalence of categories, you're going to transport that back and get a natural isomorphism between these two functors. Okay. So we're going to have like we'll have a natural isomorphism like phi right from and we're also going to have a sort of phi left from U upper star. The phi right coming from this side and the phi left coming from this side. So if we compose those two, then we'll get like,
So are you inverted for F and G?
well, no, we just said we have a fibered category.
Yeah.
And instead of inverting F and G, we impose this condition. So this is the condition which sort of corresponds to inverting F and G. So we're saying that F and G act in an invertible way in terms of in the category world. F and G act in an invertible way. I think we could even say it's an isomorphism, but I mean, in the category theory world, and that's kind of part of what's going on with this homotopy stuff, it's not really well defined to say you have an isomorphism of categories. It's only well defined to say you have an equivalence of categories. So this statement that we're saying that these are equivalences, that's what corresponds to the fact that we're trying to invert these maps. Okay? So, I mean, a fibered category over the localized object is going to be a fibered category over C with the property that the maps inside W induce equivalences. This is going to induce a natural automorphism of the functor U upper star. That's this S1. That's going around the S1. So this is the... This is the loop around the S1, and if you think about it, this is what we're really saying is that our fibered category F, it's really a functor from C into cat. But it's really a two-functor, so a functor of two categories. And if you sort of make the localized world in the world localization in the world of two cats, you have a sort of a universal property that's going to tell you that this localization, this functor factors through this localization if under the conditions that F upper star and G upper star go to equivalences. And so what I'm saying here is that this thing, that from this example, from the fact that we have a non-trivial natural transformation here, that's going to be a non-trivial two-morphism in this category. So this thing is going to be a non-trivial, the loop is a in this L in the world of two cats.
So the
way, and you have to keep track, therefore, of how they became equal.
Yeah.
To do this fiber business.
No, but F and G are not becoming equal. They're becoming invertible.
Yeah.
And so, but as it turns out, well, this is the subject of a little bit later. As it turns out, there's only one way that something can become invertible. Become invertible is unique.
I mean, U and V, not F and G.
Yeah, but U and V become equal in two different ways. Yeah. So you might say this tells us that. I mean, if you're interested in one category, then you might be interested in fibered categories. Then you might be interested in the two category of categories because a fibered category is basically a functor of two categories. And then you can see from this discussion that you're going to get a non-trivial two-morphism in the localization of this category in the world of two categories. Well, okay, then maybe the world stops there, but it's kind of easy to imagine that it doesn't. So I mean, let me just say this. So in the world of infinity categories, there's a localization operation. So if you have a category, in fact, even an infinity category and a subset of maps, you can make the localization. And what this example is showing is that even if even if C is a one category, in other words, a usual category, this localization L of CW will, in general, be an infinity category with homotopy in all degrees. Let's say in arbitrary degrees. Okay, so you might be saying, okay, but I know about localization of categories, and that doesn't show up in what I know about localization of categories. So what's going on there? So the point is that there's going to be a truncation operation. So we'll call it tau less than or equal to 1 from infinity categories back to one categories. So usual categories. And so, for example, in the case of two categories, which you might know a little bit more intuitively speaking, the truncation operation says, let's replace the one category of maps. We'll replace it by its set of isomorphism classes. So as you can see in this example, that's going to squish this non-trivial isomorphism. If we replace the one category of maps from X to Y by just its set of isomorphism classes, then the fact that U and V are isomorphic in two different ways, that information is lost. Okay? Those two different isomorphisms between U and V become the same just equality between U and the class of U and the class of V in the set of isomorphism classes. In this example? No, I think if we do that, I think it's really S1. Pretty sure. You can tell me. For general W, you get higher homotopies, yeah. We'll see that. I mean, that's related to his question about S2, as we'll see in a minute. But let me I just wanted to say this to sort of explain how this fits into what we learn about localization of categories from the classical texts, Gabriel Zisman principally. So the usual location of localization of Gabriel Zisman is a one category denoted C and then W inverse. And it's given like this. So we take So the usual localization is obtained by, and can be viewed, if you like, as obtained by first taking the infinity-categorical localization, then taking the truncation of that. Okay? So in this truncation operation, we have sort of a priori at least, we've discarded the higher homotopy information. There are, as I was saying before, there are theorems that say that you can actually recover the higher homotopy information in some cases. So in some cases, even the localized category is kind of so big, so it has like shift operations and lots of exact triangles and stuff like that in it, that rigidifies the things and that uniquely determines the thing here. So in some cases, you can sort of recover that information. But kind of as an a priori thing, you've discarded this information. And if you do that in just like a small example with just 4 objects and a few morphisms and so on, then you're really going to be discarding information. And here we've sort of created some homotopy. So I should probably, especially if there are any algebraic topologists in the audience, they'll be saying, but wait a minute, we've known this for decades and decades, which is definitely true. I mean, in a certain sense, this whole subject is just sort of, from my point of view, is kind of algebraic geometers discovering what algebraic topologists have known for a extremely long time, in many different aspects. I guess to our credit, possibly you could say that maybe the algebraic topologists didn't necessarily realize that the different things they were doing would also apply to other subjects in different ways. It could be sort of packaged together in a different way. I don't know. Anyway, but so this localization, so L of CW was constructed by Dwyer-Kahn. In fact, in 2 ways. So there's the general. There's general, and then there's what's called hammock. The hammock thing is probably the most geometrically meaningful picture, but it's kind of hard to draw on the blackboard and explain. But I mean, sometimes in literature, people will call this hammock localization. But so what is it? So in the Dwyer-Kahn viewpoint, it's what's called a simplicial category. And so this is our first, you might say, candidate for what it means to be an infinity category. So this is our first This is our first candidate for our definition of infinity category. So what's a simplicial category? So a simplicial category let's call it A, has, I seem to always run down to just like half a line above the bottom of the board. But so a simplicial category has a set of objects, which we'll call ob-A. Actually, in some places in Dwyer-Kahn's papers, they make some distinction between classes and sets and stuff. Let's not do that. If you need to worry about that, the best thing to do is usually to talk about Grothendieck universes. Best from our point of view. So you have a set of objects, and then for any two objects, we have a simplicial set A of xy. Let's call this maybe A dot of xy. So I don't want to get too much into the technicalities of simplicial sets, but the point, especially for us here, is that we should just think this is just a certain kind of space, okay? If you start trying to use actual topological spaces in this theory, I think some people occasionally say that they could try to do that somewhere, and you can do that somewhere. You get into problems with the fact that topological spaces are sometimes have kind of bad properties and stuff like that. And since we're doing homotopy theory, we're really interested in like CW complexes, but even CW complexes might not necessarily have exactly great property. So it's usually just easier to replace the notion of space by a simplicial set. And then the space that we're talking about is the realization of the simplicial set. Okay. So think of a simplicial set as a space which has some kind of triangulation into simplices. So for any two elements of the objects, we have a space. Okay. So let's just think of that as a space. And for all x, y, z, we have composition. I'm not going to write on the board the thing about the identities. There's some identities in there too, but basically composition, which is a map of simplicial sets, A dot of xy cross A dot of yz into A dot of xz. And let's recall that this is actually kind of a crucial thing that's happening at several different places in the theory, but here, for example, which is that if you take the realization of A dot of xy, the technical people will say there's different realization functors, so I guess this must be some kind of standard one, but I'm not even sure. And then we take the product with the realization of yz. This is actually equal to, this is the Eilenberg-Zilber theorem, this is the realization of the product simplicial set. Where the product simplicial set means the simplicial set where you just take the product level by level. So that's kind of the amazing thing about this Eilenberg-Zilbert thing, and that's really using the degeneracies in the simplicial set. So if ever you wondered in your life, why are we worrying about these degeneracies in the simplicial set? Those are exactly the things which make this true. That would not be true if you tried to use simplicial sets that only had face maps but not degeneracy maps. But that's quite useful here because it means that we really have a map of the product of spaces into. So you can really think of this as giving a spatially enriched category, okay? And then the condition here is just that this thing is level by level associative. But you can see from what I'm saying here, if it's level by level associative, then it's also going to give you an associative product on spaces. By the word level here, I'm talking about this dot here, which is the index of the simplicial set. Okay. Then let's just put in parentheses plus identity maps. Okay. So that's a simplicial category. So simplicial category is really a kind of a strong kind of a category enriched in spaces. And we say, okay, instead of general spaces, we like our spaces to be nicely triangulated and so on and come from simplicial sets. And as it turns out from this Eilenberg-Zilber theorem, that's actually compatible with this operation of looking at an associative composition law. Okay. And maybe before I erase this, what's going to happen here is that in our localization, in our example, if we take this L of C, if we take A dot A equals L of CW, now this is supposed to be a simplicial category, then if we look at A dot of X comma Y, this is going to be a simplicial set. This space is going to be homotopy equivalent to S1. Just tells you the picture that you see here. So that's kind of the thing which is indicating that, that there's some kind of homotopy stuff going on, even if you just started with the category. And so then you sort of notice, once you see that, you sort of notice that, oh, okay, actually in all these cases where you have some kind of intuition that there's some kind of homotopy theory going on somehow or other, you also happen to be localizing stuff by some set of maps which doesn't look like it's a set of isomorphism classes of something, like a set of isomorphisms, I mean. So for example, complexes localized by quasi-isomorphisms of complexes, but quasi-isomorphism of complexes, you can't necessarily really invert it. I mean, or spaces localized by weak homotopy equivalences of spaces, or simplicial sets. You can't necessarily invert in a unique way a weak homotopy equivalence. Okay? And even if you choose the inverse, it's not going to be inverse on the nose. There's a homotopy to be chosen. And so this is not really an accident in the sense that if you have some kind of category and you have some kind of natural subcategory like that, that you would like to declare to be invertible, well, when you do this inversion in the world of infinity categories, so for example, the Dwyer-Kahn localization, that generates homotopy. And indeed more is true, that actually generates the homotopy that you think it would generate. So that's the nice thing about this whole situation. So for example, if we take, let spaces So let's let spaces, we'll call spaces the category of simplicial sets. Okay. Then let's let W be the set of weak homotopy equivalences. I guess for simplicial sets, I think weak homotopy equivalence is the same as homotopy equivalence, if I'm not mistaken, but just to be sure here. So as an aside, let me just recall the definition. So a map of spaces from X to Y is a weak homotopy equivalence if pi 0 of X is isomorphic to pi 0 of Y, pi 1 of X maps isomorphically to pi 1 of Y comma F of X. In fact, really all the pi i's. So weak homotopy equivalence is a map which induces isomorphism on the homotopy groups. And those are the things which you want to think of as invertible in the theory of homotopy theory. Then let's let S be L of spaces W. then so I'm not making a mistake here, but so that we just have to write this down in a way which is not actually wrong. So then we would like to say S dot of x, y. What's S dot of x, y? So this is a simplicial set that represents the mapping space representing maps, the mapping space from x to y. So let's see, what's that going to precisely mean? I guess that S dot, let me see if I can, somebody in the audience will tell me if this is wrong, but S dot of x to y should actually be equal to the space of maps, the space of, so it should be weak homotopy equivalence to the space of maps from, sorry, and this is the realization of x to the realization of y. So does anybody have an objection there? There's maybe the better way of doing that, but that involves spouting out a bunch of words, which we should be comfortable with in a little while, but not necessarily, which is take the simplicial sets, assume that the y is fibrant, then you can take the mapping simplicial set. You can take the mapping simplicial set, and that's a simplicial set that should be weak homotopy equivalence to this one. Okay. But so this tells us that what we know about the homotopy theory of spaces, so we know that if we have two different spaces, there's going to be a space of maps from one to the other. That information actually comes out from this localization process.
Sorry, so what if you didn't localize the category before you tried to figure this thing?
But this is just the category, this is just a category. It's not a simplicial category. You can do another thing, which is you can make a simplicial category. So you can say you have a simplicial model category structure. So you can say let y be a fibrant object, and then take the mapping simplicial set in the simplicial model category. That's going to, again, be the same simplicial set here. Okay. But here we're just looking at the category of all simplicial sets, just in a basic way. This one? This is the Dwyer-Kahn localization. Whichever one, I didn't say what that was. I'm going to say what that is in a more, let's see how we're doing for time. I'm going to say what, maybe on the next lecture I'll say what that is, but maybe in a different model. You can say what it is. I can do that. That's why I say it's the Dwyer-Kahn localization. We can put dk here if you want. I'm saying take this Dwyer-Kahn localization operation, whatever it is. It has this good property. We're going to discuss this more, okay? Okay. I think you can look at, if you have a computer, you can look at Wikipedia and look at the definition of Dwyer-Kahn simplicial localization. That's going to be perfectly much as good, if not better, than having me write it on the board. Unless sometimes there's a mistake in Wikipedia, but okay. You have to be a little careful. Okay. So let's see what I want. So now I'd like to just get back to this comment about the two-sphere. Okay. So I guess the picture isn't here anymore, but our picture sort of suggested quite strongly that there was really a two-sphere happening rather than just a. This suggested there was a two-sphere happening. Okay, so I'd like to think of this two-sphere in the following way. So let's not worry about these other maps too much anymore, but let's look at x and y. Think of it as an actual two-sphere. And in this two-sphere, the maps are only supposed to go from here up to here, right? Because we didn't localize anything that told us to go back down to here. we only localized some stuff up here, which led to these different identifications. Okay? So it means that you're gonna. So let's picture this as we're allowed to make a path that goes from x to y, but the path is only. So here's my joke. I don't know if I'm allowed to say this on TV, but the people in the southern hemisphere built a wall that says that people from the northern hemisphere are not allowed to go back into the southern hemisphere. Okay. So you can only go from here up to here. Okay. You're not allowed to go back. Okay. So now what's the space of paths? So the space of paths from x to y under that constraint is really just going to be the S1 because it's just going to cross in just one point. Okay. So under that constraint, so if the paths just are supposed to go from down here to up here, then you have an S1 of paths. Okay. So now, how do you get the two-sphere? Well, to get the two-sphere, it's kind of clear what you want to do is you want to localize some more. So to get to S2, let's localize some more. So let's invert any one of these maps that goes down to x, but that's going to invert everybody else. Okay, so let's just invert. So let's invert all the maps, so let's let W equals C. Okay. So what happens if you take a category and invert all the maps? So now there's a kind of a question is how are we going to sort of probe this phenomena, okay? So to probe this phenomenon, remember what happened, this is erased here, but remember what was happening here? We took a fibered category, okay? But that's only going to really probe a sort of a one homotopical degree of this type of thing. So to probe this phenomenon a little more, let's look at fibrations. Well, let's look at functors from C into spaces. Let's look at functors from C into spaces, but spaces is just this bare one category of spaces. But then let's require that W, which in our case, in our example, is going to be all of C, that should go to weak homotopy equivalences, so maps. So what are we going to get if we have something like that? So I claim, if the calculations are not too off, I claim that you'll get the following type of picture. Okay, we'll sort of finish with this discussion here. So let's take the nerve of the category C. So in the nerve of category C is a simplicial set. The simplices are things of the form x0 into x1. They're sequences of arrows in. I guess this is an n simplex. They're sequences of arrows inside C. Okay. But think of this as some simplicial set. Then we have the realization of this simplicial set. So the realization is basically you take, real simplices in the sense of subsets of R to the n plus 1. You take these simplices and glue them together according to some formula depending on how the boundaries of the simplices work in the simplicial set. Okay? And now we could take f of x0 cross the simplex. Okay? And we could try to glue those things together, okay? So maybe it should be, it's either x0 or xn, depending. I think it's x0 in this case. So we can, these are spaces. So this is the simplex, and this is the simplex, okay? So these are spaces which are homotopy equivalent to just fx0. So then we can glue these together. And we're going to get some kind of space, so let's call it sort of some kind of realization. I don't really want to call it. We'll get some space. Well, I'm not really saying you have to kind of imagine, but suppose you had just suppose you just had a one simplex, okay? So you're going to have an interval, right? You're going to have a space x0, f of x0, and you're going to have a space f of x1, and you have a map from f of x0 to f of x1. So, but you want to put f of x0 across the interval, and then you glue that by the map from x0 to x1 over here. So this is probably going to look a little bit better if we assume that like those maps are all injective maps of spaces or something like that, which I think you probably can do. Depending on what the category is, you can certainly do that in certain cases. I think you usually do that. But anyway, so let's glue this together. We got something we'll call it sort of the total space of F. But it has a map to this realization of the nerve. Okay. And this condition tells us that it's actually going to be a vibration. So that's kind of a hard statement, which I definitely would not be able to explain how to prove here. Sorry?
I understand that you have these mapping cylinders, that's how you're gluing the first vector, and then how are you simultaneously gluing
Delta n, what's the n? Which n is it? 1/6 n?
No. This is when you have a simplex like that. You take fx0 across delta n. And then you sort of glue it into the ones for the lower simplices by the maps. I think you can pretty much do that, even if you don't have injective. But as I said, I'm not all that much of an expert in algebraic topology here. But basically, this condition here is going to lead to the fact that you get a vibration. With fiber f of x0 over the point. Every object, an object of C gives you a zero simplex in the nerve, and that gives you a point in the realization. So over that point, the fiber is going to be, homotopy equivalent to, weak homotopy equivalent to f of x0. We glue together these pieces. Let's draw this. To this first step, you basically have, so we have f of x0, we have f of x1, f of x0 across the interval. Then we have f of x0 across the endpoint at 1, but that gets mapped to f of x1. So glue this guy onto this guy using that map. So for example, it's better if that map's an injection, for example. So then we just sort of stick this thing on to the end of the interval. But I think even if that's not an injection, it's just going to sort of squish the endpoint of the interval a little bit. Okay. But the point is that this is going to be a vibration equivalent to a vibration. So that's a hard statement, which definitely true, up to some technical hypotheses at least. Not easy to see why, but easy to sort of intuitively see that that should be happening. Because basically we're just gluing together copies of the same space. I mean, under this hypothesis, this thing over here is a homotopy equivalent. So it's like we're taking a space, and then we're adding another space that's homotopy equivalent to this space, and then we're saying it's going to be a fibration. Okay. It's fibration up to equivalence. So well, I should be stopping here. So what I'd like to say here is that we'll start here next time. When we have a functor like this from our category into spaces, which sends W into, which in our case is all of C, sends W equals C, which sends W into maps that are weak equivalences of spaces. So it means that we're supposing we have a functor from C into spaces such that all the maps are weak equivalences. Then the claim is that you get a fibration, total space of F, over the realization of the nerve of C. And that's in our picture. This is going to be S. So in the example, sorry? Yeah, this is a point inside the nerve, realization of the nerve. Yeah, I mean, it would be suffice to say that if this was connected, but if that's not connected, then it might have different connected components where the fibers are different. Okay. So in our example, then this realization is S2. And so this is just to explain in what sense so the claim is that localization is really supposed to be S2. But we need to understand in what sense, what's it going to mean to say that the localization of the category sort of corresponds to S2 here. So I'll take off from here next time. So now the question, so we would like to say that the localization of C, where you invert all the morphisms of C, that should sort of correspond to the nerve of the category C. But then what's this correspondence? Okay. So that's the subject of next that we'll start with next time. Okay, so I'll stop here. So star, I mean, I guess star plus the condition that W, I mean, in what we're doing here, we're assuming that W equals C. So it means that all these gluing maps are actually equivalences. So if the gluing maps were isomorphisms, you would kind of obviously get a fibration. I think I'm not sure, but I think that that's one way of proving this fact is that there's this theory of minimal fibrations where if you have a map of minimal fibrations that's an equivalence, it's actually an isomorphism. But I'm not completely sure about that. Otherwise, you have to do something more complicated. And this should be in Siegel's papers, but maybe you need some theory, I think, to really do this. But kind of intuitively, it's clear that if you start gluing together spaces, chunks of spaces, and the gluing maps are always equivalences, then there's no reason of getting anything other than a fibration where those are the fibers. But you can get, non-trivial fibrations is kind of the point.
You keep talking about fiber categories and fibrations. Are you working on a monocategory you're not written as well, or is it another?
No, I mean, there are model categories that I haven't told you about yet. But by fibration here, I mean a fibration of topological spaces. When I said, well, I didn't say fibrant category. I said fibrant object in this category of simplicial sets here. Over here, I was saying why it was going to be fibrant object. There, I'm talking about a model category, which is the model category of simplicial sets, the Kahn usual one. I mean, if you want to make this precise, the easiest way to do that is to use model categories. But we'll be discussing that. I gave you one. Where did I say that? I think I erased it here. I gave you one like first candidate for the definition of an infinity category, which is a simplicial category. You can use that as a definition if you want. What we're going to see is that there's other definitions that maybe have certain advantages in terms of properties over that one. That's actually has the advantage of being the easiest one to understand. But, you know, that thing was around for such a long time, and nobody actually kind of picked it up and used it. And I'm positing that maybe one of the reasons was that it's not so easy, as we'll see, to get some of the properties that you would expect. You have to, like, do some work. That's the property, in fact, that doesn't work so well, yeah. If you, I mean, what Tony says is that if you have two different infinity categories, you'd like to define the category of functors from one to the other. That's the thing which doesn't really work for simplicial categories. So that's the reason why you need to come up with other models. But so, you know, maybe the thing to take from what we're saying today is that basically an infinity category is you've got a set of objects and you have a space of maps between two objects. So it's basically some kind of category where instead of a set of maps, you have a space of maps from one thing to another.
You can say that, you know, in a certain sense of equivalence, all the definitions of infinity categories are equivalent to this one.
Yeah, yeah. So I mean, it's perfectly good